Hello everybody, let's talk about binary search trees. So we've talked about heaps, let's move on to a different type of binary tree structure. So the way we'll start this set of slides is we'll first compare binary search trees with their biggest competitor, which would be sorted arrays. We'll sort of emphasize what does it mean to have different heights of a binary tree, and then we'll talk a lot about common search tree operations. And there will be an exercise associated with this set of slides. All right, so let's start with talking about sorted arrays. This is something that everybody's played around with before, and you have a lot more experience with this than a binary search tree or a trees type data structure. So what is important about a sorted array? Well, you just have your items like we have here, and they're in sorted order. So that makes it easier to access or to find something, essentially. Not access, but to find something. So I have a list of operations, and for each one of these operations, we are going to consider the running time. Now, instead of having a pop-up and ask you the question for each one of them, I'm going to ask you to pause the video after each one and think about it, and I'll give you about 3 seconds between me asking the running time and giving the answer. So make sure you're pausing the video and giving yourself a chance to sort of fill in the blanks of the running time column before I give it to you. All right, so for the first one, what is the running time of doing a random access? So let's say that I want to access the element 17, and I know the index. So it's called an access and not a search because I already know the index. Random access is constant time. That's one nice property about arrays. If you know where the element is, it takes a constant time to access it. All right, so how about search? Let's say I don't know where the 17 is in this sorted array. How long does it take to find it? You have two options for finding it. You can do it the naive way, which would be a linear scan. So that would be big O of n. But since this is a sorted array, we can do better than that. We can do a binary search, which is big O of log n. Just as a reminder, a binary search will first check the middlemost element, and it knows that it's not any of these. So it's going to look to the right. It'll check this element. It knows it's not that one, so it'll look to the left, and then it'll find the 17. How about selection? So as a reminder, the selection problem is how do I find the ith biggest number? So the first biggest number would be the number 3. The nth biggest number would be the number 36, and everything in between. Well, the first biggest number is at index 0. The second biggest number is at index 2, and so on. So that's a constant time operation. You just add 1 to the base 0 index. How about finding the predecessor? So here again, let's pick on 17. Let's say that... Okay, sorry about that. You may have heard the bugle horn dog bark in the background, so I lost my place here attending to that. So for predecessor, let's say that we're picking on 17 again. I think I even used that term just a few seconds ago. For me, it was like 5 minutes ago. And I want to know the predecessor. Well, let's say I know the index of 17. The predecessor is the item to the left of it. So how long does it take to say, well, I know the 17 and I know the index of 17. How long does it take to find the predecessor? And actually, we'll do the successor at the same time. The successor is the 23. Well, those are constant time because we know the index of 17. You subtract 1 from the index to get the predecessor, and you add 1 to the index to get the successor. How long does it take to access all elements? So that's what I have here for output. For example, if you want to print all elements. Printing all elements means you're going to do a linear scan through the input. So that's going to be big O of n. How about inserting an element? So let's say we wanted to insert the number 13. How long does that take? We're going to not say just for 13, but in the general case, how long does it take to insert a number anywhere in the array? Worst case. Well, worst case, I have to shift all these elements down and then put the 13 where the 17 is. And the worst case of that is trying to put a number at the very beginning, like the number 1, which means I have to shift everything down, which means we have a big O of n situation. Likewise, for delete, I could have to delete the 3, which means I have to shift everything to the left. Alright, so finally for extract min, what is the running time of the extract min? I want to get the minimum element and remove it from the sorted array. Well, it's essentially take the element out and then delete it, so it's going to have the same running time as a delete, which is big O of n.